Lesson: Adversarial Machine Learning Theories. Adversarial machine learning presents a unique and challenging dimension to the field of artificial intelligence, calling for enhanced security measures and innovative solutions. At its core, AML involves manipulating machine learning models through various techniques, which can lead to incorrect predictions or classifications. This manipulation is particularly pertinent in security-sensitive applications such as autonomous vehicles, facial recognition, and financial fraud detection, where the consequences of adversarial attacks could be catastrophic. The theories surrounding adversarial attacks and defenses form a crucial part of AI security, offering both threats and opportunities for AI professionals. At the heart of adversarial ML theories is the concept of adversarial examples inputs to a machine learning model that have been intentionally crafted to cause the model to make a mistake. These examples are often imperceptible to human observers, but can dramatically alter the model's output. One classic example is in image classification, where an adversarial attack might slightly modify a few pixels in an image of a panda, causing a model to misclassify it as a gibbon. Such vulnerabilities arise because ML models tend to learn statistical patterns rather than robust representations, making them susceptible to minute perturbations. To address these vulnerabilities, several defenses have been proposed, focusing on enhancing the robustness of ML models. One primary method is adversarial training, which involves augmenting the training dataset with adversarial examples. This approach helps the model learn to classify adversarial inputs correctly, thereby improving its resilience. However, adversarial training is computationally expensive and often specific to the type of attack it is trained against, limiting its generalizability. Tools like CleverHands, an adversarial ML library, provide utilities for implementing adversarial training and other defenses in practice. Frameworks such as the fast gradient sign method and projected gradient descent are commonly employed to generate adversarial examples, which can be used for both testing model vulnerabilities and enhancing their robustness through adversarial training. FGSM works by calculating the gradient of the loss with respect to the input data, identifying the direction that would most increase the prediction error, and then perturbing the input in that direction. PGD extends FGSM by applying multiple iterations of small perturbations, providing a more powerful attack that can reveal deeper vulnerabilities in ML models. While adversarial training and gradient-based attack methods are widely studied, they are not exhaustive solutions. An emerging area of research involves exploring the interpretability of ML models to understand why they are vulnerable to adversarial attacks and how their decision boundaries can be reinforced. Techniques such as saliency maps and feature visualization can shed light on the inner workings of models, offering insights that can guide the development of more robust architectures. Moreover, the integration of formal verification methods into ML systems is gaining traction. These methods, originating from software engineering, aim to mathematically prove that a model behaves as expected under all possible scenarios, including adversarial ones. Tools like ReLUplex and SMT Solver have been adapted for verifying properties of neural networks, ensuring that certain types of adversarial attacks cannot occur. In addition to technical solutions, a comprehensive approach to adversarial ML must also consider the broader context of AI governance and regulation. Organizations need to establish clear protocols and guidelines for assessing and mitigating adversarial risks. This involves regular vulnerability assessments, the adoption of best practices in model development, and continuous monitoring of deployed systems. Frameworks like the AI Risk Management Framework proposed by NIST provide a structured approach to managing risks associated with AI, including adversarial threats. Case studies of adversarial attacks in real-world scenarios highlight the necessity of these measures. For instance, researchers demonstrated how adversarial patches, small, inconspicuous patterns, could cause object detection systems to ignore or misclassify objects, posing significant risks for autonomous driving systems. Similarly, adversarial attacks on facial recognition systems have shown how subtle alterations to facial features can evade detection or impersonate others, raising concerns for security and privacy. To effectively counter these threats, AI professionals must cultivate a deep understanding of both adversarial techniques and defensive strategies. This involves not only technical expertise, but also the ability to anticipate potential attack vectors and develop comprehensive risk management strategies. Practical tools like Foolbox and RT offer a suite of functionalities for crafting adversarial attacks and evaluating model robustness, enabling professionals to experiment with different techniques and defenses in a controlled environment. Ultimately, adversarial machine learning theories underscore the dynamic and evolving nature of AI security. As adversaries develop more sophisticated attack techniques, defenders must remain vigilant, continuously updating their knowledge and tools to safeguard AI systems. By leveraging a combination of adversarial training, interpretability techniques, formal verification, and robust governance frameworks, professionals can enhance the security of AI systems, ensuring their reliability and trustworthiness in critical applications. In conclusion, adversarial machine learning represents a complex interplay between attack and defense, requiring a multifaceted approach to ensure AI security. Through the application of practical tools, frameworks, and strategies, professionals can address these challenges head-on, enhancing their proficiency and contributing to the development of robust, secure AI systems.